Okay, great. Good morning. So today, what we're going to do is we're going to wrap up our discussion of reduction oxidation reactions. So we'll look a little bit at oxidation numbers again, as we did last week. And then we'll look at half reactions, very simple half reactions. And then we'll get into molarity calculations. So as you start to work through the experiment that involves the titration of acetic acid and vinegar, and then what's it called? Titration of hypochlorite and bleach. Both of those experiments involve calculations that have molarity in them, concentrations. So we want to be able to get some experience doing those calculations. Okay, so that's the last section that we're going to cover in chapter 4, which is section 4.5. Okay, all right. So let's take a look at these redox reactions again. Mostly what we spoke about last week was the assignment of oxidation numbers or oxidation states. So for this next problem, that's what we'll do. We'll look at the assignment of oxidation states, and then we'll move on into the molarity calculations. Okay, so let's come up here. There we go. Oops, sorry. Yeah, but that's the one I wanted. Why that didn't show up. Let's close that. Okay. All right. Identifying oxidizing and reducing agents. So this one is just it's a little tricky because of the language. It's actually a pretty simple problem, but the language can be confusing. So the confusion is around the idea of calling something an agent, a reactant. An agent is a reactant. Okay, it's the actant in the reaction. So when something is a reducing agent, that means it's reducing the other reactant. When something is reducing the other reactant, it itself is getting oxidized. Okay, so the idea here is that a redox reaction is the transfer of electrons. So the electrons are coming from the reducing agent and going into the oxidizing agent. Okay, so when you do this, what you do is you just assign oxidation numbers, just like we did in the previous problems. But then you figure out which one lost the electrons, that's the reducing agent. Which one gained the electrons, that's the oxidizing agent. Okay, so the first one is the reaction of oxygen, O2. There's 3 moles of O2 reacting with 4 moles of iron, Fe, to form 2 moles of iron 3 oxide, Fe2O3. And we want to identify which reactant is the oxidizing agent, which one's the reducing agent. I guess there's a possibility that the reaction is not a redox reaction. It looks to me as though all 3 of these are, but if it turns out nothing changes oxidation state, then it's not a redox reaction. So that you would just select no, and you wouldn't answer the following questions. Okay, so let's take a look. Okay, so this is 302. And we don't have to worry about the states of matter. Okay, so there's our equation. Let's assign oxidation states, okay? So oxygen is our first substance over here on the reactant side. That's an element. Elements, by definition, have oxidation states of 0. So what I'm going to do is I'm just going to write down the oxidation state or oxidation number up above the symbols, and I'll put a little line there to indicate that's not an O, it's a 0, okay? So each atom in that O2 has an oxidation number of 0. The same is true for iron. Iron is an element, right? There's no charge, so it's not an ion. There's no other element. It's not a polyatomic ion. It's not a compound. It's just a symbol for an element. So that means it's 0 also. And as I said last week, you can ignore the coefficients for these types of problems. Now, when we come over to the Fe2O3, now we have a little issue here because we have iron and we have oxygen. That's a compound. So Fe2O3, that's a compound. So what we said about compounds is that when you add up the oxidation numbers of all the atoms in the compound, it's got to equal 0. Okay, so 2 irons plus 3 oxygens, those oxidation numbers have to add up to 0. Well, we don't have a rule for iron, but we do have a rule for oxygen. Oxygen is -2. So we have 2 irons plus 3 -2s has got to equal 0. 3 times -2 is -6. So 2Fe minus 6, right? Because plus a -6 is the same as -6. And then you add the 6 to both sides. You get +6, right? Remember, metals, you should get a positive. You should get a positive oxidation state for metals. You're only going to get negative oxidation states for the non-metals. There are a couple of exceptions to that, but they're relatively rare. Okay. So now you divide both sides by 2. Because we want to know how much each iron is, not both of them together. What's the oxidation state is the charge, essentially it's the charge on each atom in the substance. So Fe would then be +3. Now you can figure this out just by figuring out the charges too. Fe2O3, oxygen is -2, iron is +3, that adds up to 0 and it works. So you can do that too. So +3, remember the oxidation state, you put the sign +, negative, then the number. Sign and then the negative. And you do need to put positive. You can't just put 3. That's ambiguous. So you got to put +3. Okay, it looks like something happened, right? If you take a look at it, the oxygen went from 0 to -2. So I'm going to draw a little line there, okay? And it also looks like the iron went from 0 to +3. So that's definitely a change. So we would select that this is a oxidation reduction reaction. Now let's figure out, I'm going to show you how to figure this out. If something is becoming more negative, it's gaining electrons. So look at the oxygen. The oxygen goes from 0 to -2. So it's becoming more negative. I'll put that in parentheses, negative. If something is becoming more negative, that means it's gaining electrons. Remember, the symbol for the electron is the E negative. And the one that's gaining the electrons is the oxidizing agent. If I could spell it, oxidizing, I-N-G, agent. Okay, so you can just kind of remember that. The one that becomes more negative is the oxidizing agent because it's gaining the electrons, which means it's taking the electrons from the other agent. Okay. And then likewise, it's the opposite. Iron is becoming more positive. It's going from 0 to +2. So it's becoming more positive. So that means it's losing electrons. And by definition, that's called the reducing agent.
Is it a pretty safe bet whenever you have oxygen like this in a pretty simple equation that it's going to come out to be the oxidizing agent being oxygen? Or does that,
if you have a non-metal reacting with a metal, and those are the reactants, most of the time, the oxygen will be the oxidizing, the non-metal will be the oxidizing agent, and the metal will be the reducing agent. We generally use metals to reduce non-metals. Now, yeah, I mean, we have to be a little bit careful with that though, because there are reactions we can run where we make what occurs in nature do the opposite of what it does normally. So, you know, in a battery, when you charge up a battery, a rechargeable battery, what you're doing is you're using the energy from the circuit to make a reaction that doesn't normally occur, right? And you're making that happen to charge the battery back up. So you have to be be careful with that, because if you see a problem and someone wants to pull a trick in there and make it a reaction that, you know, they're not going to tell you that this requires energy, but it would require energy. They could show you a reaction that is the reverse of what normally happens. So it's probably better to go with the definition that if something is becoming more negative, it's gaining electrons, so that's the oxidizing agent. And then if something's becoming more positive, it's losing electrons, and that makes it the reducing agent.
Do you have an example of a problem like that?
So you could have, for example, you could do the reverse of this reaction. You could take this, and if you put in energy, then what you'll get is you'll get your 4 irons and your 3 oxygens out of that. So essentially what's happening is the iron's going +3 to 0, right? So it's actually becoming more negative. So the iron in this case is the oxidizing agent. And then the oxygen is going from -2 to 0, right? So it's going from negative to 0, that's becoming more positive. So it's acting like the reducing agent. So it just sort of depends on the direction you write the reaction, the equation.
Okay.
Mhm.
Thank you.
So now let's take a look at another example. The second one is oxygen plus ethane. Okay, so we have a little organic reaction here. So 7, they're writing this kind of in an odd way. I'm not sure why. They're writing the oxygen first and then the organic, just like they did with the iron. Again, I'm not going to write the states that matter because it's not important for us here. There we go. Okay. So again, what you want to do is you want to just look, you know, assign oxidation numbers and then see what became more positive. The one that became more positive is the reducing agent. The one that became more negative is the oxidizing agent. Okay. Again, oxygen's an element here, right? So elements by definition are 0. So that's cool. And you can actually, you know, you can flip over to the other side and do everything. You know, oxygen is always -2 in a compound, or almost always, right? So the oxygens are going to be -2 because they're in compounds there. We also have a rule about hydrogen. Hydrogen is +1, right? So we know hydrogen here is +1, +1, +1. So all the hydrogens are +1 all the way through the reaction, right? There is no change occurring to hydrogen anywhere in this reaction. But there are changes occurring to the oxygen. The oxygen, there's a lot of oxygen atoms in this balanced equation, 14 on both sides, but 0 on the reactant, -2 on the product. So becoming more negative, that makes it the oxidizing agent. Now, if there's an oxidizing agent, there has to be a reducing agent, and it's not the hydrogen, because we already saw that hydrogen is +1 all the way through. So there's only one other element left, and that's carbon. So maybe it's the carbon. So let's see. This is kind of a little tricky here. Let's take this formula here. What I'm going to do is I'm going to condense it down to C2H6, right? That makes it a little easier. When we do oxidation numbers within a compound or a polyatomic ion, the assumption is that every atom of the same element has the same oxidation number. So we're not going to have a compound where one carbon is -2 and another carbon is +2. We'll assume they're all the same. So +1, and then we don't know what that one is, but we do know it's a compound. So 2 carbons plus 6 hydrogens has got to equal 0. We know the hydrogen is +1, so 2 carbons plus 6 times +1, well, that's equal to 0. 2 carbons plus 6 equals 0. Subtract 6 from both sides, and then divide both sides by 2. Oops, I changed the sign there for some weird reason. Minus 6 over 2, and you get negative 3. So carbon is negative 3. So each of those carbons is negative 3. So I guess you could write it like that, negative 3, negative 3. Now, what about the carbon on the other side? This negative 2 is the oxidation number of the oxygen. So that's a compound again. So let's do CO2. Carbon plus 2 oxygens equals 0. Oxygen is negative 2. 2 times negative 2 is negative 4. Add 4 to both sides, and you got plus 4. So now you can see what happened. The carbon went from negative 3 in both cases here to positive 4. That's a big change. That's a difference of 7 charges. So that's pretty huge. This is a combustion reaction. Combustion reactions are very energetic and involve the transfer of a lot of electrons. Okay, so the carbon, I'll just sort of write it here. Carbon went from minus 3 to plus 4. That's a more positive. That's the loss of electrons. That makes it the reducing agent, just like I said. Okay, if you become more positive, that means you lost electrons, which means you're the reducing agent. Okay. The older terminology would be essentially that the carbon reduced the number of oxygens on the other reactant. So you had 7 O2, so oxygen was, pure oxygen, O2. Now that oxygen is with the carbon. So the carbon essentially reduced the number of oxygens in the other reactant. So it's the reducing agent, but we generally don't use that terminology anymore. Okay. All right, so there's your second one, oxidizing agent, reducing agent. Let's take a look at the third one. Third one is going back again. Well, this is actually a different type of redox reaction. This is where you have a metal and a metal compound. And this is the basis for a battery generally. Generally batteries, this is how they work. You have a metal and then you have another metal that's in the form of a compound. And so an example of that would be lithium with cobalt. So you would have a lithium element, Li, plus cobalt sulfate, COSO4, for example. That would give you a lithium ion battery. Okay. So again, we just go through and assign oxidation numbers. The difference here is that we've got some compounds. So it is useful if you want to use this method to keep in mind that, hey, that looks like an ionic compound. So you got copper 2. Right, that's copper 2, and you got sulfate. That's an ionic compound. So we could write it that way. Same thing with the product side. You got iron and you got sulfate. Sulfate's negative 2. So that means the iron's got to be positive 2. Okay. If you do it that way, what that allows you to do is to eliminate, from a redox perspective, the sulfate ion. Because the sulfate ion is exactly the same on both sides. It's SO4 negative 2 on the left side. It's SO4 negative 2 on the right side. So there's no change. So in terms of redox chemistry, we can just ignore that. It's not really changing. It's not, we're just trying to figure out what's happening in terms of redox. So that actually simplifies things quite a bit. Now you have iron plus copper 2 becoming iron 2 plus copper. Now it's really straightforward. You can actually see what's happening in terms of the oxidation states because elements are 0 and monatomic ions are the charge of the ion. So iron is becoming more positive, right? Take a look at what happened to iron. It went from 0 to plus 2. That's becoming more positive. So that's the loss of electrons. So that's the reducing agent. The reducing agent is the one that loses the electrons. The copper is going from plus 2 to 0, right? Elements are 0. So that means it's becoming more negative, right? If you become less positive, you're becoming more negative. So that's the gain of electrons. And so that means it's the oxidizing agent. And this is actually the basis of a battery, is that essentially one metal has a higher attraction for electrons than another metal. So for example, lithium has the lowest attraction for electrons, the lowest affinity of electrons of any metal in the periodic table. So that means if you put lithium metal in your battery, it's going to very much have a driving force towards giving those electrons to the other metal. You can use any other metal you want with it, so that gives you some flexibility. Lithium is really at the limit of the greatest affinity for giving away its electrons. So it's the reducing agent, okay? So if you combine it with something like iron or cobalt or nickel, then what happens is the other metal takes the electrons. And so that's what's happening here between the iron and the copper. The copper, which is positively charged, is taking the electrons from the neutral iron. Now, when you see something that's neutral, you might not think, oh, it doesn't really have that many electrons, but it does, right? A neutral atom has electrons. So if something is positively charged, there's a chance it will take the electrons from the atom that's neutral, from the element that's neutral. And so that's what's happening here. The copper 2, Cu plus 2, is taking 2 electrons from the iron. And when the iron loses those 2 electrons, it becomes iron plus 2. And now the copper plus 2 is copper. There's energy associated with that exchange. When one atom, or one ion in this case, takes electrons from another atom, from a different element, there's energy that is shifted along with those electrons. And that energy can be used to drive the electrons, to push the electrons through an electric circuit. And now you have energy that you can use to drive whatever device you want to use. Once one of those reactants has been depleted, so, for example, let's say we run out of iron, all of it's been converted to iron 2, the reaction will stop. Likewise, if the copper 2 runs out, and all of it is converted into copper, the reaction will stop. So you have to have both reactants, right? So one of them is most likely a limiting reactant. Generally, the limiting reactant is the ones that's more expensive. If that happens, then either you throw the device away, you can't use it anymore because all the reactants have been used up, or if the particular chemistry of that combination is unique, or I should say is flexible, some reactions can be pushed back the other way. So what you can do is you can take these products and put energy back in. So I'll write it like this: you're putting in energy into the reaction, and then you can push it back to the starting point. Right? So now you've recharged your battery. You now have the iron and copper 2. You can disconnect it from the charging port, plug it back into your circuit, and then this reaction will happen again. And generally there are limits to how many times you can do that. It just has to do with the particular chemistry of each element that's involved, as well as the design of the device. Okay, so lithium, it turns out, is pretty good. Lithium is actually a pretty good metal for doing rechargeable batteries. Nickel is pretty good. Cadmium is pretty good. The problem with cadmium is that it's toxic. Mercury sometimes can be used, but mercury is toxic. So if you want to stay away from toxic metals, that limits what you can do.
This is a closed system. This interaction of electrons, it's kind of like a closed system, like a battery or whatever. So it doesn't go anywhere. It just keeps exchanging these charges almost like infinite, not infinitely, because you just said that it does eventually run out of them. But I don't know. I guess if it's a closed system, which is how it sounds, how do you end up eventually running out of the ability to do this kind of thing, like batteries eventually degrade, stuff like that?
Well, there's two aspects of that. One is, it's a reaction. So just like any reaction, eventually you run out of reactants, right? So if this is such a simple equation, if I said, look, I have one mole of each, right? Well, let's make it 1 mole and 2 moles. So if I put in 1 mole and 2 moles, what happens? Well, this one reacts with this one, right? They react. So how much can react? Well, we only have 1 mole of this, right? So that means we'll react 1 mole. So we won't have any left over. We only lost 1 mole here. So we still have a mole left over. So we still have one of the reactants, but the other one's gone, right? Because now we have one, we started with 0 here. We gained a mole of each, right? Because every time the reaction occurs, you form product. So we got 1 mole of each product. And maybe that's what you're trying to do. Maybe you're trying to make some of this stuff. Actually, that's something that's done, right? So like if you want to take a metal that's dissolved in water as an ion, like gold +3, you can mix it with another metal and have it react with the metal, like with zinc, for example. The gold ions will react with zinc, converting the zinc into zinc +2 and converting the gold +3 into gold. Now you've got metallic gold that you can collect. So sometimes that's done that way. But in terms of something like a battery, this reaction's got to stop because we're out of iron, right? There's no iron left, so this reaction's done. So that's, either you throw it away, you either throw the battery away because there's no more iron left, or you recharge it, right? And if you recharge it, then what you're doing is you're just pushing, you're using energy to push it back the other direction. And now this is going to go back up to a mole, right? So now, you gain another mole of this. So now you have 1 mole left, and you gain a mole of this. So now you're back to your 2 moles. Now, hopefully that works out perfectly. Hopefully, you can regain 100% of what, you had produced in the first cycle. Usually doesn't work that well. Usually what happens is you lose a little bit each time. And again, that just has to do with like, when you're designing something that's kind of big like a battery. I mean, we don't think of a battery as being real big, but it is from an atomic perspective. Essentially what happens is there are little sections in those metals that get reacted with, oxygen might get in there, a little water might get in there and cover those atoms up, or maybe some of those atoms will dissolve into solution and they just really don't work anymore. So over time, every type of battery, no matter how good it is at being recharged, over time, some of those atoms will get displaced or covered up by something and be unable to go back and forth like they had at the beginning. So that's really an engineering issue. So if you could make a perfect, something that's perfectly sealed and no air could get in there and no water could ever get in there, and you had 100% pure metals, and you could make a layer of like 1 atom thick, and so you'd have this enormous surface area on the inside, then it might last, for a long time. But even pure metals are usually not that pure. You might be able to get 98, 99% pure lithium, but maybe 1% of it is sodium, and sodium has a slightly different chemistry. And so that sodium might interact in such a way to, cut down on the ability of that battery.
Yeah.
So
That's really interesting. Thank you. I have a friend who's an engineer and he works for like one of these major tech, development companies, and he works on batteries and like cooling systems and all that. And he's talking about like how there's a huge race in that industry to continually right now, like that's where the technology basically is just developing more and more efficient batteries, smaller and lasting longer, stuff like that, capable of producing more and more energy. So it's like, yeah, it's nice to actually understand a little bit behind like what he's doing.
yeah, it's a huge area right now, just because these, now we're putting computers into everything, right? So it used to be a computer was on your a whole room, and then it was on your table, and then it was on your lap, and then it was in your pocket. And the eventual goal is to put computers in, in
Brain.
your pencil. Your pencil will have a computer, right? And your glasses will have a computer. And so that means you need smaller and smaller computers, but you need smaller and smaller batteries, right? But you still need a lot of energy, right? Because the faster a computer is, the more energy it uses. And so you need more and more and more energy density. And there are some limits here. The problem is that chemical reactions have, a certain amount of energy content. But it's limited, it's not as much as, say, a nuclear reactor. If you could put a little nuclear reactor in your computer, you could probably run your computer for thousands of years, and maybe even a phone you could do it. But there are problems with nuclear, right? There's radiation is the main problem. But chemical reactions just only have, it seemed like a lot of energy when the Industrial Revolution started, and it seemed like a lot of energy until a few years ago. But as these computers get more and more, faster and faster, need more and more energy, we're running up on the limits of chemical energy. And so there's a lot of people have been working on batteries for a long time. You can actually go to New Jersey. There's a town called West Orange, which isn't that far. You can just take a little train ride. It's like a half-hour train trip from Manhattan. And Thomas Edison's, his original factory, his original research center is in West Orange, and you can go visit. It's a national park, and you go see these, like, all this energy he was putting into devising batteries, into developing battery technology. So it's still a big thing. Okay, so let's see. So that is all three. Okay, so let's take a look then at the last problem involving redox chemistry. There's other aspects of redox chemistry we could cover, but to be honest with you, we just don't really have that much time. And so there's just a limit to what we can do. There's a whole section on just metal redox chemistry. So the last thing we're going to do then is we're going to look at what are called simple half reactions. Simple half reactions, they're called. So writing a simple half reaction from its description. We're almost at that point in the previous example. I showed you an equation that was really simple. It's, the iron plus the copper 2 to form iron 2 and copper. So we're essentially going to look at that kind of approach to how we treat redox reactions. And the ones we're going to look at are primarily metals. Okay, half reactions are a very useful method for metal chemistry, for redox chemistry involving metals. Combustion, you can write half reactions for combustion reactions, but it's just not that useful. It's more useful just to do metal chemistry. So that's what we'll look at here. So it says here, write a balanced half reaction describing the oxidation. So oxidation is okay, be careful. Oxidation is the loss of electrons. So if something gets oxidized, that means it loses electrons. If something is the oxidizing agent, that means it's gaining the electrons because it's oxidizing the other reactant, okay? So here we're looking at the oxidation. So that's the loss of electrons. In this example, we're going from solid calcium to aqueous calcium cations. Now remember, a cation is a positively charged ion, right? Cat is positive. An is negative. An anion is a negatively charged ion. So this is going from a neutral element, calcium, to a cation, positively charged, okay? If something is going from neutral to positive, that's losing electrons, and that would be oxidation. Now, the only issue we have to deal with is that we write these equations in a very specific way. So when you're writing half reactions, what you're doing is you're writing the symbol for the element. So I'll just write M for metal. And you're writing it plus some number of electrons. I'm putting N there, meaning it could be 1, it could be 2, it could be 3. And then that is going to form the element plus that charge. So I'll write it as N minus, meaning that if you gain 2 electrons, you become a charge, you have a charge of -2. Okay, so that's how we write reduction. Reduction is where the electrons are written on the reactant side. You're gaining electrons, so we write the electrons as a reactant. You're gaining them. When we write a oxidation, we reverse it. So if I take M, N minus, and just reverse it, meaning I'm going to take this and make it a reactant, and I'm going to take these and write them as products. That's how we write oxidation. Okay, so the oxidation half reaction will have electrons on the product side, and the reduction half reaction will have electrons on the reactant side. And then really all you have to do is balance the number of charges using the electrons. Because remember, what's happening is one substance is taking electrons from the other. So if something is losing electrons, we write it this way. This is just a formalism of how you write half reactions. If it's losing electrons, you write the electrons on the product side. And then if you're gaining electrons, you write them on the reactant side. Okay. So this one, it said we took solid calcium to form calcium cations. Okay, well, okay, but we don't know what the charge is, but we can figure that out because remember, when you look at the periodic table, there are a few patterns. And the patterns are that if you're in group A, 1A, sorry, if you're in group 1A, the charge of those ions is +1. If you're in group 2A, the charge of the cation is +2. Okay. And then remember, we had a few others. We had our aluminum, which was +3. And then we had zinc, which was +2. And then we had silver, which was +1, right? ZAZ. So element number 13, element number 30, and element number 47. They made like a little diagonal there. Okay. So you may see ones like that. For all the other metals, what they're going to do is they're going to tell you what the charge is. So they're going to say it's a vanadium 5 cation. If it says vanadium 5, that means the charge is +5. Or an iron 3, they're going to tell you it's iron 3. That tells you that it's iron +3. They'll tell you the charge. So let's take a look at this one. Solid calcium. So calcium's right there. So calcium as a solid is being converted into calcium cations. Calcium is in group 2A, so it's +2. Aqueous is said. I didn't write that down here, did I? Aqueous calcium cations. Okay. So in terms of the number of atoms, this is a balanced equation. It's got 1 calcium on both sides, so that's balanced, but the charge isn't balanced. So here's one way to think about this. The way we're going to balance these half reactions is by adding electrons to the more positive side, right? Electrons are negative. So if one side is more positive than the other side, adding electrons to the more positive side will make it less positive. So if you take a look here, our charge over here is 0. Our charge over here is +2. If we add 2 electrons, those 2 electrons have a charge of -2. So now if you add the charges together, they add up to 0, right? -2 and +2 is 0. And that's exactly what it is over here. So one way to remember this is just, write the the reactant, the product with your arrow, and then add the electrons to the more positive side until the charges are equal. Having said that, I did make the point a little earlier that if you put the electrons on the product side, that's oxidation. And if you put the electrons on the reactant side, that's reduction. And that's true too. So you can also look at it from that perspective. If I put the electrons on this side, that's oxidation. And in fact, in the question, it said, write the half reaction for the oxidation of calcium into calcium 2 ion or into calcium ions. So if it's telling you it's oxidation, that right there tells you that the electrons are going to be on the product side. So there's a couple ways to do that. But some textbooks, they won't say that. They'll just write the half reaction for calcium to calcium 2 or to calcium cations, and they won't tell you whether it's oxidation or reduction. So you can figure that out just by remembering that if the electrons are on the product side, that's oxidation. If they're on the reactant side, that's reduction. And you just add the electrons to the more positive side. So let's take a look at another example. Okay, write the balanced half reaction describing the reduction of aqueous gold 3 cations. It's telling you it's reduction. They don't have to tell you it's reduction, but they do. It's going from gold 3, so that means gold plus 3, into gold 1, gold plus 1. So when you see those Roman numerals, that's telling you the charge of the metal, okay? So in this one, it's not an element, right? Both sides are cations. It's just that one has more positive charge than the other. And notice we're going from plus 3 to plus 1. That's becoming less positive. So you're gaining electrons. That's reduction. Okay. You may not remember the symbol for gold. It's aurum is the name of the element. It's really aurum. It's ancient, right? So this is going from gold 3 cations to gold 1 cations. Now it does tell you it's reduction, so that's fine. But let's do it this way. So the symbol for gold is Au for aurum. Ag is silver, which is argentinium. All right. And so this is Au for aurum. And then this is your charge, so 3 plus. And then this is gold 1, so Au with just 1 plus right there. Okay. Okay. And then the more positive side is the reactant side. It's more positive by 2, so we add 2 electrons to that side. Okay, right? 2 negatives and a positive 3 adds up to positive 1. And that's exactly what we have on the product side. I guess they're aqueous, so I should write aqueous. Okay, so this is reduction. We're gaining 2 electrons. Okay, going from gold 3 to gold 1. Let's do one more. Oh, that's interesting. Okay, so this one is going from aqueous chromium 3 to aqueous chromium 4. So chromium is Cr. So here's your charge, plus 3. And it's going to aqueous chromium 4. So that's 4 plus. Okay. Now there's only a difference of 1. And we add the negatively charged electrons to the more positive side. So this is more positive. So we add an electron. Now you can put 1 electron or you can just put electron. If it's just 1, you can just put E negative. That's fine. I usually put 1 in front of it, but it doesn't really matter. And there you go. Now, is that reduction or oxidation? This is oxidation because we're losing electrons, right? If the electron is on the product side, that means the reactant lost the electron, and that electron is going to go over into the other reactant. So, you might have copper, for example. So copper 2 might absorb that electron and become copper 1. And then if it's copper 1, it might absorb another electron from another chromium and then become copper. Okay. There we go. Let's see, that's good. All right, looks like those are all pretty straightforward. They're just having you do those. There's much more complicated ones actually out there. But it depends on which textbook. Some textbooks, they put it in this course. Some textbooks, they put it in the next course. We use a textbook that puts it in the second semester. But actually, there is one more that I want to go over here because there's one example here that's a non-metal. So let me show that one. This one's a little bit different. So let me show it. Okay, so this one, it's about bromine, right? So it says, write a balanced half reaction describing the reduction of gaseous dibromine. Now, one of the things I like about Alex is they actually use the British system of naming the diatomics. Remember, there are 7 diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So Americans typically say hydrogen, and then you just have to know it's H2, or bromine, and it's Br2. But you can also call it di, and that's helpful, right? So if I call it dibromine, right there, I know it's Br2. So I like that they do this with these problems. So let's take a look. So we're going to go from dibromine, so that'd be Br2, to bromide anions. Bromide. That's so when you see IDE, that means it's negatively charged. It's an anion. Okay. So we're going to go from gaseous dibromine to bromide ions. Anions, it says. So remember, group 7A is fluorine, bromine. I'm sorry, I forgot chlorine. Fluorine, chlorine, bromine, and iodine. And they're all -1. So the anions are -1. Okay. So we're going from dibromine. So Br2 says it's gaseous. And then we're going to bromide. Br says it's aqueous. Again, I didn't write that down. -1 because it's in group 1, group 7. So negative. Okay. Now this is a little different in that bromine is diatomic. It's a diatomic molecule. So that means there's 2 of them on the left side. So what we have to do is we have to balance the element first. So I'm going to put a 2 in the front there, right? So now you have 2 bromines on both sides. I guess what you could do is you could write a half over on the reactant side, 1/2 Br2, but then you'd end up with a fractional electron. And, generally people don't like to have fractional electrons. I'm not opposed to it, but it probably would run into a problem when you did the problem on Alex. So now here's what happens. We have a bromine, which is -1, bromide, but there's 2 of them. So that means you've got 2 negative charges on this side, right? Each one is -1, so that's -2. The other side is 0 charge, so that means we got to gain the electrons on the other side. Remember, add the electrons to the more positive side. So if something is 0, that's more positive than -2. So I'm going to add the electrons to the reactant side. And now it should be okay. Now we should have a balanced equation. So be careful, if it's a non-metal, sometimes you have to balance the atoms first and then do the electrons. Don't do the electrons first and then the atoms. So 2 bromines on both sides, -2 here, 0 here, -2 there. The charge is balanced. Again, gaining electrons. That's called reduction. Okay, and there you go. So those are the simple ones. The harder ones are where you have to, you have oxygen in there and you have these complicated polyatomic ions and you have to balance hydrogen and then oxygen and then electrons and then add them back together. It's a whole process for that. But if you take the next semester, you'll do a little bit of that. Okay. All right. Now, only a little bit of time left, but I want to show you, let's at least get started and then we'll wrap it up tomorrow, discussing concentrations of solutions. Okay, so this is section 4.5 called concentration of solution. Okay, now this is something that we do in our everyday lives for the most part, at least we do it once in a while. You can make strong coffee, you can make weak coffee, you can make really, really sweet Kool-Aid, or you can make not so sweet Kool-Aid. What we're doing is we're changing the concentrations of the solutes. So it's useful to think of these solutions as a mixture. And it could be, more complicated than this, but generally it has two components. It has what's called the solvent, which for the most part is water. Most of the time we dissolve things, we're dissolving into water. So the solvent is the substance that is in the greatest quantity. Right? If you try to pour more sugar into water than you have water, it is not going to work very well, right? So usually you have this liquid and there's a lot of it, and then you pour a little bit of something else into it. And so the substance you're pouring it into is called the solvent. So let me draw a little picture here. And then what do? We dissolve things in the water. So I won't show the water, but I'll show the stuff we're dissolving in. So it could be sugar, it could be salt, could be an acid, could be a base, could be an ionic compound, could be ammonia. But generally we dissolve something which is called the solute. And you can have more than one. So you could add sugar and salt and citric acid and carbon dioxide, and you can make it as complicated, flavors and dyes and all that kind of stuff, and make yourself some kind of soda, right? Those are all solutes. Those are all the things that are dissolved into the solvent. So the solutes are dissolved into the solvent. Okay, and again, those are typically sugars, salts, acids, bases, could be other things as well. Okay, so usually, well, I should say by definition, there's more solvent than there is solute, although that can get a little complicated. We'll use that as our assumption. Okay, so the question then is, how concentrated is the solute in the solvent? So normally what we do is we do a ratio. We do the amount of solute divided by the amount of solvent, some sort of ratio, right? A division, a fraction, or the amount of the solute divided by the entire solution, everything that's in the solution, everything that's in the mixture. So once you've got a solute and a solvent, you've got yourself a solution there, okay? So the question then is, which one are we going to use? There's a bunch of different units that are used out there. We're going to use one that's called molarity. So molarity has a symbol. It's capital M, uppercase M. And molarity is defined as the number of moles of a solute divided by the volume of the mixture, the volume of the solution. We'll use mixture and solution interchangeably. And this is in liters. It's got to be in liters. So for people that were in the laboratory yesterday, you had to do this calculation involving, the molarity of something. It had to be in liters, right? So the problem with that is that typically most of our glassware in the laboratory is calibrated for milliliters, not liters. So that means we end up having to do some, conversions between milliliters and liters. So let me write that down. 1,000 milliliters is a liter. Okay, L for liter. There's your conversion factor, 1,000, not 100. Commonly, people will think it's 100, but it's 1,000. So 1,000 milliliters in a liter. Milli is 1,000th. That's what milli means, is 1,000. Okay. So let's take a look at an example. Suppose I have 2.5 moles of hydrochloric acid dissolved in 25.00 liters of stomach acid. Okay. Hydrochloric acid is the active ingredient in gastric juice that is partially responsible for dissolving things in the stomach. Okay, the stomach's pretty acidic usually. So suppose we have 2.5 moles of hydrochloric acid dissolved into 25 liters of stomach acid. That's a lot of stomach acid. That'd be more than one person. What is the molarity of the hydrochloric acid? Okay. By the way, we're using essentially this, the amount of solute divided by the amount of solution, because this is moles of the solute, and then this is the volume of the solution right there. So we're using that ratio right there. And there are multiple ratios that can be looked at. Okay. Hydrochloric acid is HCl. So here's what we do. We would say the molarity is equal to the number of moles of the solute. There's your solute. Hydrochloric acid is dissolved in the gastric juice, dissolved in the stomach acid. So 2.5 moles divided by the volume in liters of the solution. Well, here's our solution. Here's our volume of the solution, 25.00 liters. So pretty simple arithmetic. That comes out to 0.10 and then moles divided by liters. So the units of molarity, it's actually 2 units. It's the one unit is moles and the other one is liters. However, it is very often the case that to simplify our representation of it, we abbreviate the units with a capital M. If it's uppercase M, that means moles divided by liters. So you won't actually see moles divided by liters, you'll just see a capital M. But that capital M is referring to these units right here. Okay. There's a similar unit called molality. There's only one letter difference. So you take out the R and you put an L. And it is a concentration unit, but it's a little different. Instead of being moles per liter, it's moles per kilogram. So using the mass of the solvent for that one right there. But we're not going to cover that. We'll get to that later in the course. Okay. So 1/10 of a molar, we would say. So you could pronounce this. 1/10 molar, M-O-L-A-R, like molar teeth. You have your molars and your premolars. Molar is the concentration unit. Molarity, it's abbreviation for molarity. It really means moles divided by liters. Okay. So that's just a brief little intro. What we'll do tomorrow, which is Wednesday, is we'll look at the ALEX problems on concentrations and dilutions, wrap that up tomorrow. They're pretty simple calculations, to be honest with you, but they are important. They are concentration calculations we do in different topics in the course. And for those of you going on to Chem 12, you do molarity calculations all the time. It's really important to do molarity calculations well. So we'll do some practice on that tomorrow. If there's time, I'll jump into the next topic, which is chapter 5, which is thermochemistry. It's one of my kind of favorite chapters because you're getting into the idea of energy. I love talking about energy. But if so we may have time. But if you have any questions tomorrow, if there's any problems you want to look at the beginning tomorrow, we will have time to do that because we don't have to get into chapter 5 tomorrow. We could do that on Thursday. Okay. So have a great day. And I'll see you tomorrow.
Thank you.
Bye-bye.